Hello everyone, this is Shravani and I'm going to explain about operating system of UNIT5 and the topics are free space management, grouping and counting as well. So next moving on to the slide like free space management. So the system keeps track of the disk blocks for allocating spaces to the files when they are created. So and then later these blocks can be reused. We can to reuse the space released from the deleting the files. So free space management is created, and actually this free space management is very crucial, and the system maintains a free space list which keeps track of the disk blocks that are not allocated to some file or directory. And the free space list can be implemented mainly like using the bit vector, or sometimes we can call it as a bitmap also, bit vector or bitmap. So here like this bit vector, it is a series of or it is a collection of the bits, so where each bits corresponds to the disk block, and the bit can have two values as shown here. It can have either 0 or 1. Okay, so here the 0 indicates that the block is allocated, and 1 indicates the block is free. So just you need to remember only in bit vector, so that is 0 and 1. So 0 in this is free, 1 is in this is it is allocated. So shown in this example, like suppose consider so disk where these blocks like 2 3 4, these all are free. Okay, where blocks 2 3 4 25 and 27 are free, and the rest of the blocks are allocated. Okay, next coming to 2 2 3 4, these all are free and remaining are the allocated. So if the block is free, then what it is there? If the block is free, the bit is 1, and if the block is allocated, if the bit is 0, if bit is 0 means then the block is allocated. 0 is for allocation and 1 is for free. So consider 2. So this is 0, this is 0th line, 1 and 2. So as it is allocated, so it has given 1. So after 2, next 3 is there, means this is free. As I mentioned here, it is free. Next 3 is free, 4, okay, 4, 3 and 4 and 5. Next is 6 7, they are allocated. Okay, next 8 9 10. So in this way we can identify the bit vector, means free space management, whichever the blocks are free and whichever the blocks are like allocated. So when here advantages of this like bit vector are like it is simple to understand, and finding the first free block is very efficient, and it requires scanning the words like a group of bits in a bitmap for a non-zero word. And so these two will be the advantages. And next moving on to the next slide, we are having this linked list. So as you can like linked list is like this is another approach to free space management. So here what happens, suppose if this is the disk, so if there are different blocks are there, I just want to mark it. So if this is the case, so here what happens here, so consider some are blocked. So this is not free, and consider this is also not free, and this is also not free. Okay, so just here I have shown like consider the blocks like 2 3 4. So you can, if you want, you can give the names here like 2 3 4, they are free and the rest of the blocks are allocated. So at this situation, like in the red marks are shown in the diagram, the blocks which are with the red marks, they are they are allocated and remaining are free. So if you want to allocate this free space, if you want to manage this, so what we'll be having, so just it will be linking the first block, coming to the first, and then next it links the where there is a next empty block, it will be going and searching, it will be linking this free block, and next, and it keeps a pointer to the block next pointer. Okay, so it links, and in this way the memory will be utilized. But this is not that efficient to traverse the list, because if the if the device, or if the list is very far, so it takes times in the traversing only. And each block must be read before, each block must be read before before it links. So it requires much input output time. So however, the traversing, it is not that frequent action in this linked list. So this is all about the linked list. And next, move on to the grouping. So grouping in this is like it stores the free space like listed, like I wanted to view, like this approach stores the address of the free blocks in the first free block. It stores address of the free blocks in the first free block, and the first free block, it stores the address of some blocks, say n free blocks. Out of these n blocks, the first n minus blocks are actually free, and the last block contains the address of next free n blocks. Okay, so you can see here, so this is the first block, first free block. It is a, this, just want to make a mark. So it stores a, so it is the first free block. So consider, so what it will store. So here the first block, it stores the address of some, say like consider like n blocks address will be stored here. So, and suppose if this is the last block, okay, and this last block contains the address of next free n blocks. Like suppose if I have a file with how many so this is the block with how many blocks are like 1 2 3 4 with a length. So my length is like starting is from 2, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So my file starts from 2 and the length is of 15. So 15 is my, so after 15 like blocks, my file will be ending. Okay, so this starting block, that is second block, this will be storing the n address of the remaining blocks. Okay, it will be storing the address of the remaining blocks. And next, coming to this end block, my end block, which ends up the information. So again, this will be storing the next n free blocks. So if there are any, n free blocks, if there are, suppose consider this block is free, and this block is free, so it will be storing the different address of the next free blocks, next n free blocks. So, and this is all about the groupings. And next comes for, next is like counting. So this counting is like, so it counts and keeps like how many blocks are empty, like several. So it is used for like contiguous blocks, like how many blocks are free, and how many blocks are like they're containing some information. Like this approach stores the address of the first free disk block and the number n of the free contiguous disk blocks that follow the first block. So here every entry in the list would contain address of the first free disk block and the number of n. So it just counts and keeps how many free blocks are available. So it keeps tracks of these free contiguous blocks details. And this is all about the counting. And now we are going to see usage of system calls for file management. So these are the different system calls like open, read, write, close, else, stat, and IOCTL. So now coming to this open system call. So the open system call, it is used to provide access to the file in a system, in a file system. So this system call, it allocates the resource to the file and provides a handle that the process uses to refer to that file. So a file can be opened by multiple processes at the same time, or it can be restricted to one of the process. So it all depends on the file organization and the file system. So next, coming to the next. Now we are going to the next system call, that is read. So here the read system call, it is used to and it is used to access the data from a file that is stored in the file system. Here the file to read can be identified by its file descriptor, and it should be opened using the open system call before it can be read. So next, going to the other system call, that is write system call. So the write system call writes the data from a user buffer into a device such as a file. So this system call is one of the ways to output data from a program. In general, the write system call takes three arguments. So first it will be the file descriptor, second is like pointer to the buffer. So and here at the pointer to the buffer, the data is stored in this pointer to the buffer, and third is like number of bytes to write from the buffer. So next is like I want to explain about like LSEG system call. So this LSEG system call, it is used to change the location of the read or write pointer of a file descriptor. And next and this LSEG, with the help of this LSEG system call, it can be, I mean this LSEG system call can be set either in absolute or relative terms. Okay, and next is a stat system call is a system call in Linux. It is used to check the status of a file, such as to check when the file was accessed, at what time the file was accessed. The stat system call actually returns the file attributes, and the file attributes of an inode. I mean inode refers to this Linux, basically written by they are written by the stat function. And next, moving to the IOCTL system call. So this IOCTL refers to the input and output control, and so it is used to like it is used for talking to device drivers. Like if you want to talk to the device driver, so this system call will be generated, and it will be available in most of the driver categories. And the major use of this is like in case of handling some specific operations of a device for which the kernel does not have a system call by default. And next, at last, I just want to explain about this close system call. So as the name itself indicates, the close, it is used to terminate the access to a file. So using this system call, the file is not, I mean, if we use, or if the operating system or if the program uses this system call, so the file is no longer required by the program, and so the buffers are flushed away, the file metadata is updated, and the file resources are delocated. File resources are deallocated. And that's it. And this is all about the usage of system calls for different file management. And then thank you.